Right. So in photochemistry, we discussed about NARISH 1 reaction as well as introduction part of some selective introduction on NARISH 2. So NARISH 2 is almost all, there is a requirement of gamma hydrogen that will be transferred to carbonyl oxygen, then followed by variable products are expected. So almost all three types of products are expected in NARISH 2. Cyclobutanol formation, reverting to original molecule, and one more is NARISH 2 cleavage, that is almost all equal to MECLA40. Okay. So yesterday I given mechanism even. So two types of transition states are possible, N2 pi star, singlet and triplet. Okay. Now see the evidence for that reaction. Evidence for NARISH 2. What is an evidence? First one. Suppose see, I am taking a gamma carbon. Here gamma carbon having only hydrogens. So if I make photochemical irradiation, then what happens? See, there is a cleavage takes place here, and I can put double bond. Right? So I am breaking this one, and this hydrogen will be added on oxygen, and I am putting double bond here, OH, and this is R. Right? Every time try to break bond between alpha and beta, and if you break bond here, this radical forms a double bond, right? Then break this radical, one more double bond, and this hydrogen transfer to oxygen. So now I am breaking hydrogen or not? So now reaction is very fast. It is very fast. Same reaction if I incorporate a deuterium, heavier isotope I am using. Over here I am using D and here D. If gamma carbon hydrogens are replaced by heavier atom, photochemically, what is your answer? So can I write like this? One deuterium is transferred, one more is left, then followed by, can I put double bond here? Now this is OD and this is R, right? This bond I am breaking and I am transferring to oxygen. This D comes from here to here, and this radical forms a double bond. You will get this. So now reaction becomes slow. So which indicates that definitely gamma carbon hydrogens are transferred from gamma carbon to oxygen. Suppose see, if I take deuterium in place of hydrogen, if reaction speed is remain same, on that time we can say that there is no effect of gamma carbon hydrogen. But gamma carbon hydrogen replaced by deuterium indicates that definitely this gamma carbon hydrogens are migrates from this carbon to here. So decrease in rate of reaction, here rate of reaction decreases, decrease in rate of reaction indicates that definitely gamma carbon hydrogens are migrating from gamma carbon to carbonyl oxygen. This is one evidence. Suppose if rate is remain same, this reaction rate is remain same, which indicates that, so there is no transfer of gamma carbon hydrogen. If gamma carbon hydrogen, if I replace with deuterium, reaction rate is decreases, which indicates that there is a high dissociation energy required between carbon and deuterium as compared to hydrogen. So we can break very easily, and here required more amount of energy, slow, and this is fast. That is called isotopic effect. Okay, right. Rate of reaction decreases by replacing, what we are replacing? Gamma carbon hydrogen with gamma carbon deuterium, heavier isotope, which indicates that isotopic effect is observed. Definitely gamma carbon hydrogen is migrating. That is your first evidence for NARISH 2. Rate of reaction decreases by replacing lighter isotope with heavier isotope. Replacing with a heavier isotope, reaction rate is very slow, which indicates that definitely gamma carbon hydrogen is migrating from gamma position to oxygen. That is one evidence. Next, see, I am using same gamma carbon. Here photochemically I am using methanol. Photochemically in presence of methanol, that is replaced by deuterium. Now on that time what happens? First there is a formation of intermediate. So what is intermediate involved in this one? Here OH, here radical, and here also one more R, and this is radical. 1,4 biradical. So when 1,4 biradical responsible to give original molecule, if it is come back to original molecule, see, if I break here, this hydrogen migrates from here to here, you will get original molecule or not? If this hydrogen migrates from here to here, you will get this. Same way, during hydrogen migration from here to here, deuterium from solvent also migrates here. When deuterium migrates, what is your answer? This is double bond O, and what is this? This is deuterium, and one hydrogen is left. Out of two hydrogens, only one hydrogen is present, which indicates that solvent effect is also observed on gamma carbon. If gamma carbon hydrogen, out of two hydrogens, one of the hydrogen replaced by deuterium indicates that definitely gamma carbon is responsible for hydrogen transfer. So what is intermediate now? 1,4 biradical. Suppose if this hydrogen migrates from here to here, you will get original molecule or not? So whenever if this hydrogen migrating, during this migration, solvent deuterium also migrates here. On that time will you get this or not? So formation of this product indicates that it is a common intermediate. Definitely hydrogen migrating from gamma position to carbonyl oxygen. You will get this. So two evidences. One is replacing heavier atom on a gamma carbon, then replacing with a solvent deuterium on gamma carbon. See, when we use any deuterium on solvent, it is not replacing any other carbon hydrogen. It is targeting only which hydrogen? Only gamma carbon hydrogen it is targeting. This deuterium is not taking on beta, it is not taking on alpha, it is not taking on any place. Now deuterium is added on which position? Deuterium is added on only gamma carbon. It is not adding on this carbon, anywhere it is not adding. Why it is strictly adding on gamma? Because intermediate is 1,4 biradical. That is evidence. So that's why revertible. Yesterday I given revert to give original molecule. Reverting. Third one. So this is one more evidence. This is carbonyl group. Here I am writing thick line, and here I am writing dotted line. This is methyl, and this is ethyl, and this is normal hydrogen over here. So here 1, 2, 3, 4, 5, 6, 7. Total 7 carbons are there. So I can write S plus 5 methyl, fifth carbon having methyl, and C, second carbon having ketone. So I can say heptanone. This molecule name is S plus 5 methyl. Configuration is S. Here S configuration. So fifth carbon having methyl, and this carbon having a configuration that is S, and it is dextro molecule. So this molecule having a gamma carbon, alpha, beta, gamma. So when this molecule on photochemically irradiated, initially you will get N2 pi star singlet. So when you get N2 pi star singlet, this is methyl, this is ethyl, and here it is hydrogen. So now it is get activated into N2 pi star singlet like this. Now from there onwards, two possibilities are going to be expected. So what is your first possibility? Gamma hydrogen transfer to give radical directly, see. So from here onwards, you may expect direct product. You may expect NARIS 2 directly. So what is NARIS 2 product? Put double bond here, and this is OH. Break this one. This is alpha, beta, gamma. Gamma hydrogen transfer. Now break bond between alpha and beta. Put double bond and see. This carry like this. So here I am writing double bond, methyl, and this is ethyl, right? If you break this bond, and if you break this bond and this bond, you will get double bond, and this carry double bond. So this is a direct NARIS 2 product, NARIS 2 product from N2 pi star singlet. So from here, see, I am converting into intersystem crossing. When you go for intersystem crossing, what will you expect? Now this is methyl and this is ethyl, and here I am writing hydrogen. So now N2 pi star triplet I am writing. N2 pi star triplet. After getting N2 pi star triplet, now hydrogen transfer takes place from here to here. So when hydrogen transfer takes place, this is methyl and this is ethyl. Can I write OH here? This is OH. Here radical and here one more radical like this. Can I? So when you write two radicals after writing 1,4 biradical, it is a triplet state or not? What is the spin of two electrons? Spin of two electron is clockwise and here clockwise. Clockwise and clockwise. Okay. So next possibility. Suppose see if this electron goes to opposite side. Now this is reversible inverting of electron spin. Here you will expect OH and this is clockwise. If I write methyl left side, ethyl left side, then what about see? This will comes anti-clockwise. This is anti-clockwise, here it is a clockwise. These two possibilities are expected. Okay? So two possibilities, remember, whenever, if this hydrogen migrates its original place, see, if this hydrogen one more time come back to original place, then what is your answer? Now, you will get C double bond O, and what is this? Methyl, ethyl, and here hydrogen, right? Reverting to original molecule after 1,4 biradical. Then see, this hydrogen one more time come back over here. Then what is your answer? Can I write like this? This is C double bond O. This is methyl and this is ethyl and here it is hydrogen. Right? So what is the configuration of this one? This is R configuration. And what is this? S configuration. Initially what I used? S configuration. S configuration isomer I used. So this is almost all 100% or 100 grams are there. Now after this what happens? See, you will get 50 grams of this one, and what about here? 50 grams of this one. So where you observe this one? Racemization. In racemization, first how much I taken? First I taken only 100 grams of one enantiomer. One enantiomer I taken in racemic mixture. So this is going to react with photochemically, and that is going to give two enantiomers with equal amounts. Initially what is the percentage of S isomer? Percentage of S isomer is initially 100. Right now it is how much? 50, and this is 50. So what about the ratio of these two? 50-50. 50-50 means what is this? Racemization. So in NARIS 2 reaction, racemization takes place only with triplet excited state. With singlet excited state it is not possible. Directly NARIS 2 cleavage. But whenever, if it is converts into N2 pi star triplet, this N2 pi star triplet responsible to give mixture of two. Retaining spin, inverting spin. These two are equally establishes. And if it is reorganized to original molecule, 50% of original molecule, 50% of original molecule and remaining 50% of opposite molecule. So, racemization in NARIS 2 cleavage is possible only when if excited partner is a triplet state. This point is very important. N2 pi star singlet never give racemization. So getting this racemization indicates that even N2 pi star triplet is also responsible to give this. And see, after getting triplet, NARIS 2 cleavage also possible directly. So what is NARIS 2 cleavage? See, can I write directly? This is double bond OH and here it is double bond methyl and this is ethyl. Can I get this? This is NARIS 2 and here one more, cyclization. What is cyclization product from intermediate? So Here I am writing 4 carbons. This carbon carry OH and this is methyl. And see, this carbon carry ethyl below the plane and methyl above the plane. See, how many products total? 1. What is first product? Reverting to original molecule. So is it original molecule or not? But original molecule not 100%, not 100 grams even. I am taking original molecule, I am converting into singlet directly in R-2. If singlet converted to triplet, this percentage decreases. Why this percentage decreases? Because when singlet converted to triplet, reverting to original percentage is how much only? 50 grams. Now remaining 50 grams belongs to second enantiomer. So these two will be established at equilibrium. So racemation possible at N2 pi star triplet. This is very important for racemation. At which excited state NAR2 reaction undergo racemization? Either singlet state or triplet state. Only at triplet state they undergo racemation, because see, whenever if you go for singlet state you will get only clockwise and it cannot be undergo inversion of spin. See, whenever if you break this one, inter-system crossing, now you are getting triplet or not? So when you get triplet, initially you will get this one. One is clockwise. Triplet or not? What is clockwise? Triplet. Clockwise, anti-clockwise, singlet. So when these two electrons are come close together, this electron undergo inversion. So this is 50%, it is 50%, both will give 50-50. This is called racemization. So racemization of NAR2 possible only when if you take triplet state. Singlet state racemation is not possible. It is one more evidence that definitely reaction proceed with a 1,4 biradical intermediate. See, without this impossible to generate these two. Suppose if you are getting only one intermediate, you will get this as a 100 gram. But this 100 gram converted to 50 and 50, which indicate that one is a triplet, other is a singlet. After formation of this triplet, they will invert their spin. After inverting the spin, these two possibilities are 50-50. Now racemation is possible. So NAR2 also undergo racemation only in presence of N2 pi star triplet state, not in singlet state. Because singlet state already spin is same. See, suppose if it is a singlet state, if this hydrogen migrates, what is your answer? See, it is already clockwise. Here this is ethyl and here I am writing methyl. Now what is the spin of this electron? This is anti-clockwise. 1,4 biradical in their singlet state, after transferring hydrogen, you will get two opposite spins. So when you get two opposite spin, they will combine directly. And what is your answer? You will get directly cyclobutanol. This is OH, this is ethyl and this is methyl, and C, this is Me. Directly cyclobutanol formation takes place. There is no racemation. Because these two are already having opposite spin, they never undergo inversion. Focus on this electron. This electron having opposite spin or not? When two having opposite spin, directly they will combine. If they combine, you will get this. And if they dissociate, see, if they dissociate clockwise, anti-clockwise. And here anti-clockwise, here clockwise. So these two break together, you will get these two. If these two combine together, you will get these two. There is no formation of racemation. But in this case, after getting triplet, suddenly you will get two electrons with same spin. When two electrons at same spin, they won't combine. They won't give this directly. Why? Same spin electrons never combine together. So on that time, whenever if they are coming very close together, this electron undergo opposite spin due to electron-electron repulsion. And one more due to CC rotation, two possibilities are expected. So this percentage will be decreases and this percentage will be increases. So racemization possible at which state? Triplet state only. Racemation is not possible at singlet state. Why means? What is the reason? In singlet state after hydrogen transfer, 1,4 biradicals having opposite spin. They are responsible to give NAR2 cleavage and cyclation directly because opposite spin is dominating. But here see, after hydrogen transfer, you will get a triplet state. When two electrons having same spin, triplet. So triplet electrons never combine. It is very slow. So whenever if they want to combine together, suddenly this electron goes to opposite side. That will give this one. So this is 50% and this is 50, you will get racemic mixture. Clear? So that's why racemization is also one of the evidence for this particular concept. So racemization possible only at which state? So solvent effect is observed, isotopic effect is observed, even respiration also gives information that definitely 1,4 biradical intermediate, singlet state directly gives cyclation and NARIS2, but triplet state it will give cyclation, NARIS2 and one more is racemic mixture. If I take only one enantiomer initially, it is enantiomer right now. E1 that becomes E1 and E2. So two reactions are possible, singlet as well as triplet. See, when singlet is participating in reaction, if they revert to original molecule, you will get 100 grams one more time. Possible. Respiration is not possible. If it is 100% inversion takes place, so singlet state you will get 100 grams of this one as it is, if they not give this two. If they not give this two, this will be recollected one more time, 100 gram in singlet state. But once if they convert it to triplet state, we can't convert this same isomer into 100 gram. We are converting it to how much? Only 50 gram. What about remaining 50? Second enantiomer. Means 100% these two are enantiomers. Means if you want to prepare one enantiomer to other enantiomer, racemic mixture, definitely there is a requirement of triplet state. Singlet state, NARIS2, cyclation, reverting, all are possible. But reverting, you can recollect 100 grams. Reverting 100% possible. But reverting will not give second enantiomer. But here reverting will give second enantiomer. Both isomers are 50-50. See, whenever if it is giving 100, these two are not possible. If these two are 100, these two are not possible. Right or not? See, if it is 100 gram, final also 100 gram, this is not contributing to give answer. So now two states you need to focus. Singlet state, triplet state. Be careful. Singlet state, there is no respiration. Whichever enantiomer if you take, if it is revert to original molecule, you get same enantiomer. This is E1. If singlet state if I use, you will get E1 100 gram. But here see, E1 50 gram, E2 50 gram. So when you get reverting to original molecule 100 gram means these two are not possible. If you get this is 50%, this is 50% means these all are not possible. So here you write in N2 pi star singlet state, reverting of reaction leads to single enantiomer. So here reversion means when reaction is going backside, you will get only single enantiomer, even. Okay. What about in case of N2 pi star triplet? In N2 pi star triplet state, same, reverting of reaction leads to racemic mixture. This is called racemization. So racemization possible at which state in Norris 2? Racemization possible only in triplet state. This point asked in gate exam. This point is important for gate exam. Even set exam also this statement is given. Norris 2 reaction, racemization possible in which state? Singlet, N2 pi star singlet, N2 pi star triplet, pi 2 pi star singlet, pi 2 pi star triplet. 4 options are given. N2 pi star triplet only, not pi 2 pi star triplet. Here you need to focus. These two you need to focus for getting racemic mixture. Next, fourth one. Last evidence with substitution evidence. See, here I am writing aromatic group. This is AR and alpha, beta, gamma. Photochemically I am irradiating. On the time you will get AR plus 1 olefin and then cyclobutanol formation, right? So this is Norris 2, this is cyclation, Norris cyclation. Now here alpha position I am writing 2R. Here I am writing R and here also R. If I write R and R, now these two carbons carry R and R. Okay? Then see if this carbon carry alpha. So here can I write 2 R's or not? This is R and R. Alpha carbon, you target alpha carbon. So if you focus 1, 2, 3, 4, this is 1 and this is 4. 1, 2, 3, 4. Okay? Suppose see, if R and R is equal to hydrogens, all are hydrogens. Otherwise R and R dash. R dash you write down. R dash is equal to hydrogen. On that time see, here these two one product, this is one product. This is almost all 89%, this is only 11%. This is your first possibility. So R is equal to methyl, I am writing, and R dash is equal to hydrogen. So on that time see, this is 71% and what about here? This is 29%. See, is it cyclobutanol percentage is increases by substitutions at alpha position or not? Initially R and R are hydrogen. If R and R are lighter atoms, on that time Norris 2 is most important as compared to cyclation. Norris 2 is major, Norris 2 cleavage is major as compared to cyclization. Now R is a methyl group, R dash is hydrogen, means initially no substitution. Next case is one substitution. On that time see, 89 converted to 71. Percentage is decreases for Norris 2 cleavage. Now see, third possibility, R and R dash both are equal to methyl groups. Two methyls are taken. Here R and R dash both are methyl groups. On that time what happens, see, this is only 11% and this is 89%. See, you need to remember this reaction. If this alpha carbon having only one substitution, on that time NAR2 cleavage is major, cyclation is minor. Suppose if this carbon having no substitution, still NAR2 is major. So this is NAR2 cleavage. You write clearly NAR2 cleavage, and what is this? Cyclobutanol, cyclization or young cyclation. Cyclobutanol is major when alpha carbon having a two substitutions. If there is no hydrogen, if two substitutions are present, blindly write down this is major. On that time this is exists, but percentage is very less. So be careful. NAR2 reaction always depends on alpha substitution. If alpha substitution having lighter atoms, two hydrogens are present, on that time this is major, these two. So olefin formation, enol formation is major. Suppose if one substitution is alkyl, other is hydrogen, on that time this is major. If two are alkyl, on that time cyclobutanol is major, on that time this is minor. Clear? You need to remember this. In NAR2, always remember focus on cyclobutanol. Normally they won't ask this because it is normally McLafferty rearrangement only. Right. Clear? See how it is possible. I will show here. Here two substitutions are present. First case, two hydrogens are taken here. Now photochemical irradiation. Now here one of the hydrogen will be activated. Here hydrogen you can take N2 pi star singlet like this. Here this hydrogen migrate from here to here. So after migration of hydrogen, what is your answer? Here radical, and this is AR. So this is AR and here AR. So you will get one count for biradical or not? Now this 1,4 biradical, see, this is alpha carbon having no substitutions. So this I can write like this. See, this is alpha carbon overlap, and here see, hydroxy and aromatic ring, here it is a biradical. Two biradicals are there. So can I write this two? Here two electrons are present, that is sigma overlap. This is carbonyl 1, 2, 3, 4. Alpha, beta, gamma. Now see, this is this carbon 1, and next is 2. This is 2 and this is 3. Between 2 and 3 there is a sigma bond, is there or not? Then followed by 4. Now what happens? See, whenever if you want to get cyclobutanol, when it is possible? Cyclobutanol formation when these two radical orbitals are overlap. Okay, suppose see, these radical orbitals and 2 and 3 sigma bond. So is it a C alpha or not? C alpha, and what is this? C beta. This bond I am saying, this bond. Now this sigma bond and these orbitals are both are in one plane. So 4-membered ring, this is C2, C3, and these two radical orbitals are in one plane. When this radical orbital and sigma bond overlap, both are in one plane, what happens? See, sideways overlap is increases. This overlap is called sideways overlap. So when sideways overlap is increases, then automatically what happens? This bond, formation of double bond formation takes place. Here there is a double bond. So now this sideways overlap responsible to break this bond. Then what happens here? This radical forms a one more double bond. So what is this answer? NOR/2 or not? It is NOR/2 cleavage. So here NOR/2 cleavage is dominating. Now next thing is, see, suppose see, these two are overlapping now. These two are overlapping. What is this overlap? This is called linear overlap. Linear overlap, and this is called side-on overlap. Sidewise overlap, linear overlap. Here linear overlap is there. See, if sideways overlap is very strong, this linear overlap is weak. Linear overlap is strong when these two are not exist. So whenever these four orbitals 1, 2, 3, 4 all are in one plane, what happens? See, sideways overlap is stronger than linear overlap. When sideways overlap is stronger than linear overlap, what happens on that time? This is sideways overlap. This is sideways overlap and this is linear overlap. Sideways overlap is strong only when these two radical orbitals and sigma bond both are in one plane, like this. Both are in one plane. On the time cyclobutan formation takes place or not formation takes place. See, sideways overlap is strong. This is more attracted. It is also more attracted. On the time this bond is weak. If this bond is weak means I can break here or not. I can break here and here and I can get NOR/2 cleavage. So this product formation is minor. See, linear overlap. When linear overlap takes place, you will get this product. Is it right? See, if this orbitals, this orbital and this orbital are in one plane, sideways overlap is stronger than linear overlap. If sideways overlap is very stronger, you will get NOR/2 cleavage and this percentage is minor. So now I can say this is major, and what about this one? This is minor. So these four orbitals are in one plane only when if there is an absence of substitutions at alpha carbon. See, is it alpha carbon? Alpha or not? Is there any substitution? No substitution. When there is no substitution, there is no crowding interaction between these orbitals and aryl ring. See, alpha carbon, no substitution. There is no crowding between aryl and these two. Here hydrogen is there. No crowding. If there is no crowding, these all are in one plane. So when all are in one plane, then definitely sideways overlap is very strong, linear overlap is weak. When sideways overlap is very strong, NOR/2 cleavage is major. So when linear overlap is very strong, sideways overlap is weak. When linear overlap is very strong, cyclobutanol is major. So now, why these four orbitals are in one plane? Why these all are in one plane? Why? Because there is no steric crowding between alpha carbon substitutions and carbonyl carbon substitution. Is it alpha carbon? Alpha carbon having 2 hydrogens. Now they are very small atoms. If these two are very small atoms, this hydrogen and aryl, there is no crowding. If there is no crowding, these all orbitals are in one plane. So indirectly what I am saying is, here hydrogen is there, here hydrogen, and here also hydrogen is present. Between this hydrogen and aryl, there is no crowding. This aryl is a carbonyl substitution. Aryl is a carbonyl substitution. So this substitution and this carbon, if crowding is absent, you will get a linear arrangement over here, planar arrangement. All are planar. So when all are planar, sidewise dominates linear. On that time nor is true. There is no cyclobutanol formation. This is minor. Suppose if I take second possibility. Just listen, don't write. See, this is your second possibility. This is aryl ring, and here I am writing 2 methyl groups here. Methyl, and here it is methyl. Alpha, beta, gamma. Photochemically irradiated. C double bond Ar. Here this is methyl, and here one more methyl. Now here hydrogen atom is present. It is alpha, beta, gamma. So if this hydrogen transfer from here to here, then what will you expect? Can you get radicals or not? This is methyl, and here methyl, and this is 1, 4 radical. 1, 2, 3, 4. Okay. So now after getting this C, this I am writing in one more way. This is OH, and this is Ar. This is sidewise overlap, and here one more radical is there. Here one radical, here one more radical. Okay, this is radical, and here one more radical. Can I say 1, 4? But what is the difference between these two? Here I can write 2 methyls here. Okay, now this aryl ring and this methyl having a crowding. Now this is called sidewise overlap. Sidewise overlap, this is sidewise overlap. Okay, and what about this one? This one is a linear overlap. See, whenever if there is a crowding between alpha carbon substitutions and carbonyl carbon substitution, then definitely there is a crowding establishes between these two. On that time, these radical orbitals are little away from planarity. They are little bit above. Initially this is linear like this. This is also linear. These two are linear, this is linear. But right now in this case I am saying this is linear. But due to this substitution crowding with this, now these two orbitals are lifted like this. They are lifted like this. Okay. Now in this case these 4 are linear. 4 are linear like this. These 4. This orbital, this and this all are linear. But in this case what happens, see? Due to crowding with this methyl and carbonyl substitution, now these are lifted little bit away. See, these two are linear. Now this is lifted like this. Which means this and this any overlap? This is called which overlap? Sidewise overlap. What is this overlap? Linear overlap. Whenever these two are moving away from planarity, this two overlap is strong, this two overlap is weak. So, if that is the condition, then what is your answer? So, what you will expect if this is observed? See, here double bond, and here methyl, and here methyl, and this is olefin. So, I can say this is minor. I am saying it is minor. And what about in this case? Next case? Next case is cyclobutanol formation. This is Ar. So, Me, and this is Me. So, this is found to be major. So, when major is possible, which overlap is stronger than, which overlap is observed very stronger here to get cyclobutanol is major? Linear overlap. See, if linear overlap is stronger than sidewise overlap, cyclobutanol is major. This is possible only when these two orbitals are moving away from plane as compared to this one. These are completely planar. It is not planar. So, this is looks like this. This is little bit away like this. This orbital is like this. This orbital is like this. In above case, what happens? Both orbitals are like this only. Both are planar in first case. Now here this is planar. These two are not planar. Why they are not planar? Because of this crowding. So that's why alpha carbon substitution will decide the answer for cyclobutanol. If any alpha substitution is there, non-planar arrangement increase the linear overlap. When linear overlap is very strong, this is weak. then automatically you will get this answer. Suppose if this is strong, this is weak, you will get cleavage. You will get this cleavage here. Okay, so that is the importance of alpha carbon substitution. Right. First you take this. You write up to here. You write up to here. You complete up to here. So then I will give some statements. Then you write this one. Don't write completely. You write only first reaction. Linear overlap, sideway overlap. So it is also called side on overlap or sideway overlap. Pi bond formation is sideways. Sigma bond formation linear. You need to know which is linear overlap and which is sideways overlap. Sideways overlap, pi bond. Linear overlap, sigma bond. This is linear overlap, so you will get sigma bond. Sideways overlap, you will get pi bond. This is pi bond, this is sigma. Here also sigma, pi. Here also pi is there. Sideways overlap, pi. Linear overlap, sigma. Head-on overlap. Head-to-head overlap, linear overlap, axial overlap is called sigma. Side-on overlap, perpendicular overlap is called sidewise. Right. Here write one point. See, if carbonyl compounds having absence of alpha carbon substitutions. If carbonyl compound having absence of alpha carbon substitutions, 1,4 biradical produce planar arrangement of biradical orbitals and C2 C3 sigma overlap. Biradical orbitals and C2 C3 sigma overlap. This is C2 C3. So these are planar. That will produce planar arrangement of biradical orbitals and C2 C3 sigma bond. So in this arrangement sideway overlap stronger than linear overlap. In this arrangement, sideway overlap stronger than linear overlap leads to formation of enol comma ene as a major product. So here this is a major product in this case. Ene and enol is major. Means NOR-2 is major. NOR-2 cleavage is major. Cyclation is minor. NOR-2 major. In this arrangement, sidewise overlap stronger than linear overlap. That will leads to formation of enol comma ene as a major product. So in this case, which one is major? NOR-2 cleavage is major. Cyclobutanol formation is minor. Then write that second reaction. Second reaction same. Up to here it is remain same. Only thing, alpha carbon there is no methyls in first case. Second case you write down 2 methyls. planar arrangement with biradical orbitals and C2C3 sigma bond. So after arrangement of this, sideways dominates linear overlap. So on that time Norris-2 cleavage dominates cyclation. This first statement, Norris-2 dominates cyclation if there is no substitution. So no substitution at alpha carbon, no crowding. So that's why planar arrangement. So see this is above, now orbital is like this, and below dotted line indicates that one more orbital below like this. It is also little above and this is below. This is horizontal like this. These two are horizontal. This is little vertical. But in last case all are horizontal. You complete up to here. This is major and this is minor. Over. So write this point. If carbonyl compound having alpha carbon substitutions, 1, 4 biradicals produce non-planar arrangement. Non-planar arrangement. Non-planar arrangement with biradical orbitals and C2C3 sigma bond. This is non-planar arrangement. Now this and this are non-planar. Statement remains same, but only thing is having alpha carbon substitutions. If carbonyl compounds having alpha carbon substitutions, this biradicals will produce non-planar arrangement. This is a key point. In last case, planar arrangement. Right now, non-planar arrangement between these orbitals and these orbitals. Now, these orbitals and these orbitals are non-planar. This is horizontal. This is little vertical. Horizontal and vertical. So, in this arrangement, sidewise overlap. This is sidewise overlap. Sidewise overlap is weaker than linear overlap. Why it is weaker? Because there is no planar arrangement. In this arrangement, sidewise overlap weaker than linear overlap leads to formation of cyclobutanol as major product. Cyclobutanol as major product. This is called cyclation. Young cyclation is major when alpha carbon having substitution that will develop a non-planar arrangement of biradicals and sidewise overlap. orbitals. So this is the reason why they develop non-planar arrangement. Why they develop planar arrangement? Reason is alpha carbon substitutions develops steric roding with which one? Alpha carbon substitutions develop steric roding with carbonyl substitution. So due to that steric roding, orbitals are moving away from planarity. Alpha carbon substitution develops steric roding with carbonyl substitution. Carbonyl substitution is benzene. C double bond O is called carbonyl substitution. Okay, and produce non-planar arrangement of orbital. When these are non-planar, when these all are non-planar, this is linear, this is little vertical. On the time this overlap is weak. So now head-on overlap is strong. When head-on overlap is strong, cyclobutanol is major. Clear? So that are the evidences for getting reverting into original molecule Norris 2 cleavage and cyclobutanol. Right, one point. See, if carbonyl compound having variable gamma CH groups follows reactivity order. It will follow reactivity order. If variable gamma carbons are present, it will follow reactivity order. So tertiary gamma carbon is more reactive. So weakest bond as compared to secondary gamma carbon hydrogen, then followed by primary gamma carbon hydrogen. This reactivity order you need to follow. If more than one gamma carbons are present, whichever gamma having more carbons. More carbons mean tertiary. So means this bond is very weaker as compared to this and this. It is a reactivity order. More reactive means more weaker bond. If carbonyl compounds having variable gamma carbon hydrogens, that will follow following reactivity order. C. This is carbonyl group. Here R I am writing, otherwise you write Me. So photochemical irradiation I am doing now. So what about this carbon? Alpha. What is this? Beta. Which is gamma? Above is gamma. It is also gamma. But which gamma should I take? Above or below? Above. This should be taken. Okay, because it is secondary. And what about this? It is primary. Between secondary primary both are given. Secondary is more reactive. So use this hydrogen. If I use this hydrogen, can I break bond between alpha and beta? Every time remember, break bond at alpha beta. Break bond at alpha beta, put double bond between beta gamma. While putting double bond, put double bond between beta gamma, alpha carbon and carbonyl carbon. So which bond should I break here? Can I break this one? So if you break here, put double bond between beta gamma, then put double bond between alpha and carbonyl carbon. Then you will get this answer. This is major. Clear? Try to write the answers fastly. You apply the code. Write down labeling alpha beta gamma. Write labeling alpha beta gamma. First you break it alpha beta. First you break alpha beta. After breaking alpha beta, beta gamma double bond, alpha carbonyl double bond. This and this double bond, this and this double bond. Enough. And this carbonyl you convert as OH. Target alpha beta. If you target alpha beta, your answer is over. Now see this. Here I am writing a selective group now. So photochemically, what is your answer? You can take N2 pi star singlet, triplet, both are possible. Now what is this? Alpha, beta, gamma. What is this? Gamma. Now what about this carbon? Tertiary. Then what is this? Primary. First break here. First write down labeling, break it. Now after breaking, what is your answer? Double bond between. Where should I write double bond? Gamma, beta. Beta, gamma, double bond. Break this. Here already methyl is there. Then put double bond between alpha and carbonyl. Carbonyl carbon, you write down OH and this is methyl. That is the answer. You apply the shortcut. When NAR is 2 given, first you break bond between alpha, beta. See, this is your first bond or not? Which bond you are breaking? First bond you are breaking or second bond you are breaking? That's why it is called NAR is 2. What is NAR is 1? First bond you are breaking. You remember this, otherwise you don't know which is NAR is 1, which is NAR is 2. In your exam you will confuse which is NAR is 1, which is NAR is 2. NAR is 1 means we are breaking first bond. NAR is 2 means we are breaking second bond. That's why name given as 1 and 2. If anybody asks in interview, they will ask like this only. What is NAR is 1? Means don't define completely. Breaking first bond in carbonyl compound is called NAR is 1. He can understand, he won't ask any question. NAR is 2 means we are breaking second bond. If I break this bond, what is this? NAR is 1. You can remember very easily. NAR is 1 means first bond breaking for carbonyl compound. Second bond breaking is NAR is 2. Break second bond. Put double bond between second carbon, third carbon. Put double bond between second carbon, third carbon. Put double bond between first carbon and carbonyl carbon. That is the answer. Very easy. If you know this technique in rings, you can attempt to answer very easily. Otherwise, rings are very headache for you. What is the technique? Put double bond between beta carbon and gamma carbon by removing one hydrogen on gamma carbon. And one more, put double bond between alpha carbon and carbonyl carbon. Put one double bond between here, put double bond one more here. Wherever you are breaking, above one double bond, right side one double bond. That's it. And carbonyl you just convert into alcohol. This is methyl. Here ethyl I am giving. Photochemically, what is your answer? apply shortcuts. Remember mechanism, but while applying answer, apply shortcuts. Shortcuts never give any mistake. But if you want to write answer according to mechanism, you will do mistakes. Mechanism for evidence. So don't try to remember mechanism every time. Remember shortcuts. Write down mechanism one time, leave it. Sometimes mechanical questions also asking in exam. That's why remember mechanism only one time. But permanently remember shortcuts. How to predict answer? That is most important. What are the miscellaneous conditions? What is major product? Now, is it alpha? Alpha, beta, which is gamma? Above is gamma or not? Is it below gamma? Which is preferred gamma? Below or above? Below. Then can I break bond at alpha, beta? Then which should I prefer here or not? Break this carbon hydrogen. Then where should I put double bond? Either below beta gamma or above beta gamma? Below beta gamma. So above is unaffected. Below beta gamma double bond. Write down this. Then put double bond between these two. Here gamma, over here. That is the answer. Whichever gamma hydrogen we are using, that gamma hydrogen, carbon, beta carbon, put double bond. Put double bond between these two, wherever hydrogen is elevated. When nourish 2 is not possible, then only nourish 1 is possible. Don't apply nourish 1 when nourish 2 is exist. Because breaking is very easy then, breaking at respective position. So alpha, beta, here gamma, here also gamma is there. Which is preferred? Below or above? Below. Here there is no gamma hydrogen first of all. So we need to use this hydrogen. So break alpha, beta, break this. Put double bond here. Put double bond here. So between benzyl and tertiary, which is preferred? Benzyl. Benzyl is more preferred as compared to tertiary. Benzyl gamma carbon hydrogen is more preferred over tertiary gamma carbon hydrogen. So you need to break here alpha, beta, gamma. Break this bond and break this bond. If you break above hydrogen, So which is preferred? Here see, alpha, beta, left side gamma, alpha, beta, gamma, right side is also gamma is there. Then which side? Right side. So right side means left side should write as it is or not? So here you put double bond, right OH, I am breaking here. So put double bond, beta and gamma, this. So where, whichever direction we are selecting alpha, beta, there you need to break. Alpha, beta, first to target, break bond between alpha, beta, that's why NAR is 2. 2 indicates second bond from carbonyl. Second bond from carbonyl we are breaking. So this is second bond, this is first bond, this is second bond, that's why NAR is 2. Now see, alpha, beta, gamma, which one is preferred? Right side or left side? Left side. Left side means, can I break left side? Left side second bond we need to break. Put double bond between gamma carbon and beta carbon. Put double bond between alpha carbon and carbonyl. Then write down OH. Then write down right side part as it is. It is a major fragmentation. This is further undergo tautomerism. Will give carbonyl. It is further give one more NAR is 2. But initially most familiar fragmentation is this one only. Suppose if I write tautomerism, will you get C double bond O CS3 or not? Then alpha, beta, gamma. One more time, this reaction is already shown in McLaughlin. One more time, NAR is 2 possible. But this is a predominant reaction. Now see, this is given in CSR. Is it alpha? So can I break right side or left side? Left side only, alpha, beta, gamma. This is not benzyl. Benzyl gamma, it is a beta. Alpha, beta only, there is no gamma. Gamma carbon hydrogen is not there. In fast you will break right side. That is the problem, that's why they given. Now in this one, actually you think like this. Alpha, beta, gamma, see, alpha, beta, gamma, which side? Right side. So break here, put double bond between this two and this two. Be careful with these two molecules. If this is given, break left side. Why it is not possible? There is no gamma carbon hydrogen. It is not benzyl carbon of gamma. It is a benzyl carbon only, but benzyl beta carbon. So what is your answer? Here this is double bond. Here double bond OH. Here alpha, beta, and this is pH. Even esters also possible to give this reaction. This is ester, photochemically, alpha, beta, gamma. Esters. Alpha, beta, gamma. Esters can give even NAR is 2. break at alpha beta, put double bond between beta and gamma. So break here, every time break here, alpha, beta, gamma. Right. Write down one point. In conformationally rigid molecules, gamma carbon hydrogen closer to carbonyl oxygen involve in reaction. Suppose if it is not closer, no reaction, especially for rigid conformers. In conformationally rigid molecules, gamma carbon hydrogen closer to carbonyl oxygen involve in reaction. Only for rigid molecule. So this is a rigid, this is C double bond. So photochemically, what is your answer? It is a rigid conformer. When tertiary butyl is there, rigid, unable to move. Unable to move, any conformer is called rigid conformer. Now this conformer unable to move. When any conformer unable to move, whichever gamma carbon very close to carbonyl, only that will transfer hydrogen. Suppose if gamma carbon is present, hydrogen is present, but it is not conveniently available, no reaction. Now see, this is alpha, beta, gamma. Is it gamma 2 hydrogens are available or not? Is they are very close to oxygen? Yes. Now break this, transfer here, write down NOR is 2 product. Now whatever technique I am giving, based on that you can predict the answer. Can I put double bond between alpha carbon and carbonyl? Put double bond between alpha carbon and carbonyl, and this becomes alcohol. Now can I break bond between alpha and beta? Can I break? After breaking, put double bond between beta and gamma. So you need to write separately, beta, gamma, double bond. So here NOR is 2 is not exist. In this one see, alpha, beta, gamma all are available. Gamma carbon is present, gamma carbon having 2 hydrogens, but it is not available for carbonyl because carbonyl is below, gamma carbon is above. Always gamma carbon and carbonyl very close to each other if it is a rigid conformer. Rigid means, what is the meaning of rigid? Unable to flip. Flipping is not possible. Means this corner is above, they never come downward direction. This corner is below, they never goes to upward direction. So conformer is not possible. Other conformer unable to create, it is molecule where complete rigid structure is observed. So if it is a rigid molecule, unable to give next conformer. Rigid conformer NOR is 2 is possible only when gamma carbon hydrogen is very close to carbonyl oxygen. So use this and give the answer. So this is flexible, reaction possible. See, is there any tertiary butyl in this one? No. On that time it is flexible, possible to react with all gamma carbons. Now tertiary butyl is there, it is rigid. It is a rigid. Now tertiary butyl I am giving, it is rigid. What is the answer? Now, is it alpha or not? Alpha, beta, gamma. Will you write the answer? Only technique can help. If you want to write according to mechanism, it's over. Impossible to write. Break bond at alpha beta, second bond breakage. Now, so break here, put double bond here by writing outside, put double bond between these two. Will you write? Now see this one. Is it alpha? Alpha, beta, gamma. Gamma having one hydrogen. Can I break that hydrogen? Yes. So break this hydrogen. And where should I break? I should break it alpha and beta here. So between gamma, beta, there is a double bond. Now this alpha and carbonyl, there is a double bond. And this is OH. Then this is pH. Here tertiary butyl is as it is. That is the answer. Apply the technique, then you will get clear answer without any hesitation. Put double bond between alpha and carbonyl by breaking alpha beta. Put one more double bond here. See, finally in your exam, here they will write C double bond O. C double bond O, pH they will write. Enol form, that is. Enol form converts to keto form. So in exam they will write like this. So this is double bond 1, 2, and here they will put C double bond O, and here they will write pH. That is the answer. Enol form converts into keto form. Enol to keto. Enol form converts into keto form. So finally in exam they will give like this only, they won't give enol form. But you practice with enol because it is very easy. Alpha beta breakage, double bond between alpha carbonyl, double bond between beta gamma. Now see this. Is it gamma is there? Alpha, beta, gamma is there. Is it rigid? Yes, tertiary butyl is present. It is a rigid conformer. But gamma carbon hydrogen is not conveniently oriented towards carbonyl. So there is no NAR-2. NAR-2 not possible here. If NAR-2 not possible, NAR-1 possible. Now it is NAR-1. For this molecule apply NAR-1 only. Don't apply NAR-2. NAR-2 not exist. Why? Why NAR-2 not possible? Gamma carbon hydrogen is not available. Hydrogen is present, but it is not conveniently available. See, gamma carbon hydrogen is available for carbonyl. See, carbonyl hydrogen very closer for rigid molecule. Condition for rigid molecule is gamma carbon hydrogen and carbonyl. Both are very closer. Suppose if they are not closer, no reaction. NORIS 2 not possible, NORIS 1 possible. Can you write NORIS 1 product? Write down NORIS 1 product for this one. What is NORIS 1 product? Can I break right side? No. Can I break left side? Yes. So if you break left side, tertiary butyl as it is, then followed by, you will get alkyl radical, acyl radical. This is acyl and this is alkyl. Put double bond over here, hydrogen transfer, then you will get this one. Transfer of hydrogen from alkyl to acyl. You will get that answer. What is this? NORIS 1 or NORIS 2? NORIS 1. By watching the molecule you need to decide. They won't mention specially. Occasionally they will mention NORIS 1, NORIS 2. If it is a rigid molecule, gamma carbon hydrogen is present but not available. On that time NORIS 1 is possible. C double bond O pH. Photochemically, what is the answer? First you identify what kind of reactions you will expect. Possible NORIS 2, alpha, beta, gamma. This gamma having hydrogen. See, last one molecule I given, there I am saying NORIS 1 is possible, not NORIS 2. But here NORIS 2 possible here. Why NAR is 2 possible in this one? NAR is 2 possible in this molecule. Why? Last molecule, I am putting a tertiary butyl, I am saying it is not possible. Right? There I give an example just now. I am saying this molecule not involved in NAR is 2. But right now I am saying it is NAR is 2 possible. Why? These undergo ring flipping. If they undergo ring flipping, they will give this molecule. This is on ring flipping, will give this one. These two are same. They are flipped isomers. When ring flipping is possible, NAR is 2 possible. Even though hydrogen is not conveniently available. Now this hydrogen is not conveniently available, but still possible to involve in NAR is 2. So give the answer. So break it, alpha, beta. Remove this. So can I put double bond between beta, gamma? Here it is OH and this is pH. Here also same. Answer remains same. Alpha, beta, gamma. NAR is 1 possible or NAR is 2? It is a rigid decalene. Decalene is rigid. So NAR is 1 only. No NAR is 2. NAR is 2 not possible. Now here NAR is 2 possible. Because alpha, beta, gamma. Gamma hydrogen is available. Here gamma hydrogen is there, but they are not available for this one and it is not involved in flipping. No flipping. Inconvenient gamma hydrogen, NAR is 1. Photochemical symbol they given and they are asking the answer. What is the answer for this? Whether it is NAR is 1 or NAR is 2. So how to write NAR is 1? Break bond it over here. Then transfer this hydrogen here, put double bond this here. So put double bond, write hydrogen here. Now here, can I put double bond here? So one ring is as it is not affected. Now beta, gamma, double bond. Alpha and this here OH and this is pH. This is given in DL exam. What is the answer? So is it alpha carbon? So beta and this is gamma. Here tertiary butyl. This is pH, OH and this is CS3. This is the answer. What is that? Is it NAR-H2 reaction? Yes, cyclobutanol. When cyclobutanol is measured, if alpha carbon having no hydrogen, is it alpha carbon having no hydrogen? Yes, this carbon having no hydrogen. So on that time which is measured? Cyclobutanol is measured. Simply transfer gamma hydrogen to oxygen. Gamma hydrogen to oxygen, put a bond between gamma carbon and carbonyl carbon. That is the answer. Cyclobutanol is measured when alpha carbon having no hydrogen. Cyclobutanol is measured only when you will expect cyclobutanol measure when carbonyl carbon alpha having no hydrogen. It depends upon alpha carbon only. This is also CSR question. These two are repeated. Is it NAR-H1 or NAR-H2? Class